So if you are sitting still in your chair, are you moving? Well, relative to the floor, you are not. But the earth, of course, is spinning on its axis, and you are moving with the earth. So indeed, you are moving quite fast relative to a point outside the earth. The pilot of an airplane can read the airspeed indicator on his compass heading to get his velocity, but this velocity is relative to the air surrounding his plane. What if he is flying into a considerable headwind? That will certainly affect how fast he is going relative to the ground. And if it's a crosswind, that will affect his direction with respect to the ground. So we're now going to look at how we can relate motion relative to one frame of reference to another frame of reference that may be moving relative to the first. If a particle P is moving with a velocity relative to a reference frame A, and the reference frame A is also moving with a velocity relative to a second reference frame B, we can relate the velocity of P to frame B by the velocity of P to frame B equals the velocity of P relative to A plus the velocity of A relative to B. So for example, suppose you're walking on a moving walkway at an airport terminal. Let A be the frame of the moving walkway and B be the frame of the ground. Your velocity relative to the ground is your velocity relative to the walkway plus the velocity of the walkway relative to the ground. All right. So that fits with the equation above. Now, if we ever need to reverse the order of the subscripts, we just take the negative. So the velocity of frame A relative to B is equal to the negative of the velocity of frame B relative to A. So notice in the first equation, the velocity of P relative to B equals the velocity of P relative to A plus the velocity of A relative to B. Notice on the right side of the equation, we have the A subscripts are in the inside and the P and B subscripts are on the outside. And then on the left side, we just have the P and B subscripts. So if you want to eliminate one frame between the two, so for example on the right, we eliminate the A and we end up with the P and the B, which are on the outside. So in problems that are more complicated, if you pay attention to the order, the subscripts, they can help you arrange the velocities. For simple ones like the walkway, it makes sense. Right? So for the example with the walkway here, it makes sense. If you're walking on the walkway, your velocity relative to the ground is velocity relative to the walkway plus the walkway to the ground. Here's another example with an illustration. We have three cars. Car A is parked by the side of the road. Car B is moving to the right at a constant 90 kilometers per hour, and car C is moving to the left at a constant 60 kilometers per hour. We're going to attach a coordinate system to car B, and that's the x prime, y prime. We'd like to find the motion of car C relative to car B. Alright, so I've written down the given information. The velocity of A relative to the ground is 0. The velocity of car B relative to A is 90 kilometers per hour, and the velocity of C relative to A is negative 60 kilometers per hour. The negative sign is because it's moving to the left, so we're calling the left negative and the right positive. Alright, so we want to find the velocity of C, car C, relative to car B. So someone riding in car B, what would be the velocity of car C that they observe? So first let's write the positions. So the position of car C relative to A equals the position of C relative to B plus the position of B relative to A. And you can see that in the illustration. So XCB is the distance of car C relative to B, and XBA is the distance of B relative to A. And so you can see right from the diagram that the distance from A to C is XBA plus XCB. All right, now to get the velocities, we take the derivative with respect to time. So d dt of xca gives us the velocity of c relative to a, and d dt of xcb gives us the velocity of c relative to b, and d dt of xba gives us the velocity of b relative to a. Now we want to solve for the velocity of c relative to b, so I get the velocity of c relative to a minus the velocity of b relative to a. And now we can plug in the numbers. So the velocity of c to a is minus 60 kilometers per hour. The velocity of b to a is 90, but we're subtracting that, so we have minus 90 kilometers per hour. And so the velocity of c relative to b is negative 150 kilometers per hour. So this is how fast car C would appear to someone riding in car B. Now, note the order of the subscripts in the problem above. If we want to change the order of the subscripts, we reverse the sign. So the velocity of B relative to A equals the negative of the velocity of A to B. So what does that mean? Well, the velocity of B relative to A is what A would observe B moving, right? So what if you're riding with B, what's the velocity of A look like to you? Well, it looks like it's moving. If you're riding in car B, A looks like it's moving to the left at the speed that you are traveling relative to the ground. So that part is correct. All right, so what happens if there's an acceleration? So we're going to consider B is moving at a constant velocity, but C has an acceleration, meaning he's changing his velocity. Note the acceleration is the same in each reference frame. So let's look at the math, look at the equations. Okay, so we'll start with in the middle here. We have the velocity of C relative to A equals the velocity of C to B plus the velocity of B to A. Take the derivative with respect to time to get the accelerations, and we get d dt of the velocity of C to A gives us the acceleration of C relative to A. And then we have d dt of velocity of C relative to B gives us the acceleration of C relative to B. And d dt of B to A is 0 because the velocity of B relative to A is constant. So since the velocity of B relative to A, the derivative with respect to time is 0. So then we see that the acceleration of C relative to A equals the acceleration of C relative to B. So if the reference frame attached to B is moving at a constant velocity with respect to the stationary reference frame A, both reference frames measure the same acceleration for car C. So even though A is stationary in the ground and B is moving at a constant velocity, someone in car A would measure the same acceleration of C as someone in car B would measure for car C. So both A and B measure the same accelerations for car C. So this is an important consideration. So if the moving reference frame is moving at a constant velocity, it will measure the same acceleration as someone in a stationary reference frame. All right, let's look at an airplane flying when there's a wind. So we have an airplane with an airspeed of 200 kilometers per hour, flies in an area where there is a west wind of 50 kilometers per hour. The pilot wants to travel due north. So what heading should the pilot take, and what will be the ground speed of the plane? All right, so if you get in the plane and you just start flying due north, what's going to happen? Well, the west wind, that means a wind coming from the west, will blow you to the east and you'll be off course. So if you really want to travel due north, you have to fly into the wind a little bit so that if you fly away from due north, so you have to fly a little bit toward the west so that that west wind will carry you back toward due north. So you have to account for the wind. So how do we do that? Well, we do that by applying vectors. So remember that the airspeed for an airplane means how fast it can fly relative to the air around the plane. So if the pilot just points his plane due north, the west wind will carry him off to the east, and he will miss his destination. So he has to fly a little bit into the wind and let the wind carry the plane back to a due north course with respect to the ground. So we have to account for the wind. Alright, so we want the velocity of the plane with respect to the ground. So that will give us both the ground speed and the direction. We want that to be due north. So we draw that vector, the velocity of the plane with respect to the ground, and that's shown in blue in the diagram. We want that to point due north. Alright, then that's going to equal to the velocity of the plane with respect to the air plus the velocity of the air with respect to the ground, which of course is the wind. So since the wind is blowing from the west to the east, the pilot wants to go due north, so we have to point the plane toward the west a little bit so that the wind carries him back. So we have the velocity of the plane with respect to the air vector shown in green, and the velocity of the air with respect to the ground, which is the west wind blowing towards the east. We want the green vector plus the red vector to add up to the blue vector. Now notice in this situation, we end up with a right triangle. Okay, so this makes it simple to solve. So the velocity of the plane with respect to the ground then is one of the legs of the right triangle. So that's going to be equal to the square root of the velocity of the plane with respect to the air squared minus the velocity of the air with respect to the ground squared, and then square root that. So we plug in the numbers and we get that the ground speed is 194 kilometers per hour. Now to get the angle that the plane must point, we take the inverse sine of the opposite side over the hypotenuse. Well, the opposite side is the 50 kilometers per hour for the wind. The hypotenuse is the 200 kilometers per hour for the airspeed. And then we get an angle of 14.5 degrees. So the plane is going to have to fly a heading of 14.5 degrees west of due north. And then he'll end up going due north with respect to the ground. And his ground speed is only 194 kilometers per hour. So this was a simple case because we end up with the wind's velocity with respect to the ground and the plane's velocity with respect to the ground form a right angle. Now what if they don't form a right angle? So we'll look at an example with that next. Alright, so now we have an airplane with an airspeed of 150 kilometers per hour, wants to fly to a city due north. The wind is reported to be 50 kilometers per hour from the southwest. So from the southwest means it's going to be at a 45 degree angle with respect to due north. Okay, so all the southwest and northwest are at 45 degrees angles, and same thing with northeast and southeast. Those all form 45 degree angles with the compass headings. So what heading should the pilot take, and what will be his ground speed? Okay, so the ground speed then is going to be the the ground velocity vector is going to be the sum of the plane's velocity vector with respect to the air and the wind velocity vector. So we need to add the plane velocity vector with respect to the air and the wind velocity vector with respect to the ground equals the velocity of the plane with respect to the ground. So that diagram is shown here. So we want the green vector plus the red vector equal to the blue vector. But we don't have a right triangle in this case, so now we have to find the components of the vectors. So our resultant is going to be the blue vector, the velocity of the plane with respect to the ground. We know the wind velocity vector. So since the velocity of the plane with respect to the ground is due north, it's not going to have an east-west component, so there's no horizontal component. So that means the horizontal component of the plane's air's velocity vector is going to be equal and opposite to the wind velocity vector. So those two horizontal components sum to 0. So again, to go due north, the horizontal components of the wind velocity and the plane's air velocity must be equal and opposite, so they sum to 0 because there's no horizontal component for the velocity of the plane with respect to the ground. The vertical components of the plane and wind will add to give the ground velocity. The heading can be obtained from the inverse sine of the horizontal component of the plane's air velocity over the air speed. You can see that from the triangle in the diagram. So the velocity of the air with respect to the ground in the x direction equals the velocity of the air with respect to the ground times the cosine of 45 degrees, and that gives us 35.4 kilometers per hour. So the velocity of the plane with respect to the air in the x direction has to be 35.4 kilometers per hour. And then we get the angle that the plane has to point as the inverse sine of 35.4 over 150, and that gives 13.6 degrees west of north. So the plane is going to have to head into a direction 13.6 degrees west of north so that he ends up going due north with respect to the ground. Alright, so now we want to get the ground speed, so we take the velocity of the plane with respect to the ground in the y direction, so that's going to be the velocity of the plane with respect to the air cosine of 13.6 degrees plus the velocity of the air with respect to the ground of sine of 45 degrees. So those are the two y components. And then we plug in the numbers and we get 181 kilometers per hour. So he's going a little bit faster with respect to the ground than he can fly into the air because the wind has helped pushing him to the north. The wind has a component that points towards the north, and so that adds to his air speed. Alright, what if we want to row a boat across a river that has a current? So we're going to look at that now. So this is very similar to a plane flying with the wind. A girl wishes to row a boat across a river to a point directly opposite her on the other bank. She can row at 2 kilometers per hour with respect to the water. So that's how fast she can row. And her speed that she can row is relative to the water around her. But the water is also flowing at 1 kilometer per hour with respect to the banks. So what angle with respect to a line from her starting point to the point directly across the river should she point her boat? And B, what speed with respect to the ground will she travel across the river? Now, if the river were not flowing, if it was still water, she would just point her boat directly across and row across, and she would go at 2 kilometers per hour. But the water is moving, so since there's a current, so she has to point her boat upstream, and then the water flowing in the river will carry her back to the line directly across. So just like the plane flying with a crosswind has to point into the wind a little bit in order to go directly and due north, Now she has to point upstream a little bit. Also, since her boat is pointing upstream as she travels across the river, she's actually rowing a greater distance than if she were going straight across with still water. So she's going to actually go a greater distance than if she's going to actually row a greater distance than she would if there were no current and she just went directly across, because she's rowing upstream and it's the water that carries her back. Okay, so here we have the diagram. So she wants to go directly across the river. That's the dotted line in the diagram. And assume we have parallel banks here. And the current is flowing to the right. So she has to point her boat upstream, and then the current will carry her back to the line that goes directly across. So we want to find the velocity of the girl with respect to the ground. And so we have the velocity vector of the girl with respect to the water plus the velocity of the water with respect to the ground equals the velocity of the girl with respect to the ground. And again, in the equation there at the bottom, our final equation, notice the order of the subscripts. The water subscript is on the inside, the girl and the ground are on the outsides on the right side of the equation. So notice the diagram that we have here. She wants to go directly across, and the current, of course, is flowing at a right angle to the direction that she wants to go across. And so we have to row upstream a little bit in order to go directly across. And so in the vector diagram, we have the velocity of the girl with respect to the water forms the hypotenuse of a right triangle. So the velocity of the girl with respect to the water pointing upstream, the velocity of the water with respect to the ground, which of course is the current, flows parallel to the banks, and the velocity of the girl with respect to the ground, we want to go directly across, forms the other leg. So the velocity of the water with respect to the ground is one leg, the velocity of the girl with respect to the ground the other leg, and the velocity of the girl with respect to the water forms the hypotenuse of the right triangle. The velocity of the girl with respect to the water is how fast she can row. That's the 2 kilometers per hour. The velocity of the current is 1 kilometer per hour, forms one of the legs. So then we can see from the diagram, the angle that she has to point upstream then is going to be the inverse sine of opposite over hypotenuse. So that's 1/2, which of course is 30 degrees. So she has to point her boat 30 degrees upstream in order to go straight across. Now to get how fast she travels with respect to the ground, we just apply the Pythagorean theorem, solving for one of the legs. So we have the square root of the 2 kilometers per hour squared, which is the hypotenuse, minus the 1 kilometer per hour squared. And 2 squared, of course, is 4. 1 squared is 1, so we have 4 minus 1, which is 3, or the square root of 3, which gives us 1.7 kilometers per hour with respect to the ground. Also notice that she's going to go a greater distance than if she simply rowed straight across. If she just pointed her boat straight across and rowed, she would travel a shorter distance with respect to the water and would get across faster, but the current would carry her downstream and she would miss the point where she wants to go. So with the current flowing, she has to row upstream and let the water carry her back to the point directly across. So she's actually going to row a greater distance with respect to the water. So it's going to take her longer to get across the stream, but she ends up going straight across where she wants to go. Now we're going to look at how we describe circular motion. So if a particle is moving along a curved path, there is always an acceleration. Even if it is moving at a constant speed, the velocity is still changing direction. And so there is a change in the velocity, which means an acceleration. So even if we're not speeding up or slowing down, we're traveling at a constant speed, if we're changing direction, our velocity vector is still changing. So that's an acceleration. The first case we'll look at is uniform circular motion. This is motion along a circular path with a constant speed. So only the direction of the velocity changes. Thus, the acceleration vector points at a right angle to the direction of the velocity and toward the center of the circular path. All right, so if we have an acceleration along the direction of motion, we speed up or slow down. If acceleration points in the direction of our velocity, we speed up. If the acceleration points opposite to the direction of the velocity, we slow down. If the acceleration points perpendicular to the direction of the velocity, we cannot speed up or slow down. We just change direction. So that's the case we're going to look at here. So the acceleration vector points in the direction that the velocity vector changes, which is toward the center of the circular path. So this kind of acceleration we give a special name, and it's called centripetal acceleration, or A with a C subscript. And it can be shown that the centripetal acceleration magnitude can be written as v squared over r, where v is our speed, r is the radius of the circular path. So if we're moving in a circle at a constant speed, the magnitude of the centripetal acceleration is v squared over r. And notice that that's constant. However, the direction is not constant. The direction is always toward the center of the circle. So the acceleration vector is rotating. So it's constantly changing direction. But the magnitude of the acceleration stays constant, v squared over r. All right, now the particle moves a distance around the circle equal to 2 pi r, right? That's the distance around a circle is 2 pi r. So the total distance we travel in one complete circle is 2 pi r. So we can relate the velocity as a distance over time. So we take the total distance once around the circle is 2 pi r, and the time to make one complete circle is called the period, and we use capital T to represent the period. So that would be the time in seconds. So 2 pi r is the distance around the circle divided by the time to go once around the circle will be our velocity. Remember, velocity is distance over time. So T is called the period or the time to complete one revolution. All right, now we'll look at the second case where we have motion in a circular path when the speed is not constant. So we could be speeding up or slowing down. So for speeding up or slowing down, there must be a component of the acceleration vector along the direction of motion, which is tangential to the curved path. So our acceleration vector has two components. One perpendicular to the motion, which is toward the center of the circle. That's the centripetal acceleration. And the other one, the tangential acceleration, which is perpendicular to the centripetal acceleration and tangential to our circular path. So we can write the we can write the acceleration vector as the sum of the two components, the centripetal acceleration plus the tangential acceleration. The tangential acceleration describes our speeding up and slowing down, while the centripetal acceleration tells about the change in direction. And since the centripetal acceleration is in the radial direction, you'll often see it written as simply the radial acceleration using an r subscript instead of the c subscript. Okay, so later on in this series of videos, we'll look at some problems with centripetal acceleration. But for this time, we just wanted to describe the circular motion. So that comes to the end of this video. So in future videos, we'll go on and we'll look at the causes of motion, which of course are forces. And then we'll talk about Newton's laws of motion, which describes how forces affect motion. So I hope to see you in future videos.
Hi, Dr. C here. Thanks for viewing this video, and please help support this channel and subscribe. Also, please leave your comments, questions, or suggestions, and I thank you for your support of this channel. I've also included a link to the next video in this series.